Well, I would like to start by saying a few remarks on action at a distance in curved space-time, in the space-time that is normally discussed by general relativists. So, one can see that there will be a lot of problems when one actually wants to have a theory which will reflect action at a distance at speed of light in curved space-time. So, let us see what happens. So, if you take two world lines A and B, and in the flat space-time what you do is you take any point here, you draw the null cone which goes here. So, if you call it A and B, then you can define the square of distance A square AB, and in fact in general for any 2 points you can define an S square AB, and only for null rays will this be 0. So, when you write delta of S square AB to indicate that you are talking of action at a distance at the speed of light, so that here this interaction which is defined by delta S square AB, you remember I had written up that integral for this which was something like it was something of that kind. There was an EAEB, the charge. And what we wanted to emphasize in this integral was that the only contribution will come to it when S square AB is 0 because of the delta function. So, taking this clue, we can ask what will happen in curved space-time. So, we can try to keep the same formalism, but generalize it to curved space-time. So, first we notice you can of course have the world lines defined as defined as lines in 4-dimensional manifold. What you can do is take any 2 points A and B, then what you have to do is this here in Minkowski space-time was a very simple connection from here to there. It was a straight line in Minkowski space. In curved space what will happen is you have to compute for any 2 points the geodesic which connects them, hoping that there is a unique geodesic which will connect A to B. And then you have to integrate ds from A to B along that geodesic to get the value of S, and obviously and then you square it and then write delta of S square AB. Now, it is conceptually okay to think of this formalism, but you will see it will be tremendously difficult to handle in practice, because for any general space-time it will be hard to tell what the GIK should be and what the geodesics are like. You have to solve a second order differential equation or set of 4 differential equations which are nonlinear. So, it will become a very complicated thing, and still after getting defining this, you will find that you are not able to reproduce Maxwell's equations in curved space-time or Maxwell-like equations. So, why does this happen? So, first let me take this flat space-time example. Why it works in flat space-time is because the wave equation satisfied by delta S square, let us call it x a. That means I am taking x as a general point, a is a fixed point, and S square x a is defined, and that this delta is a delta function of that, and you apply the wave operator with respect to x. So, this turns out to be equal to minus 4 pi delta 4 x a. That means, if you take the 4-dimensional delta function which identifies x, the 4 coordinates here x with the 4 coordinates a. So, this delta function will give you something only when x is actually equal to a, x is at a. So, this result, which is sometimes called the Dirac identity, you can try to prove it by actual Fourier analysis. It is not too difficult, it is a little involved, but you can do it and prove this. Actually, since its identity, I would put it 3 equal to sign. Now, this result is true in flat space time. So, you might think that if I define my curved space time S square and put it inside delta function and change this box, the wave operator, from flat space time to the curved space time, which is all easy to do. So, if you then apply this in curved space time, you will find that this is not equal to this, that is does not give you such a simple result in curved space time. So, if you are looking for generalization of action at a distance to curved space time, at first you will think that you have hit an obstacle which is hard to remove. So, you might say that therefore, I must give up the attempt. The answer is no, you have to be a little more clever. This was the case in flat space time. Now, when you seek its generalization in curved space time, what you do is you put it here and there will be a root minus g, which comes from the metric determinant of curved space time. So, I am defining the wave equation in curved space time, and this is basically, once you see this, you will say this is nothing but, and that is the reason for using this g, it is Green's function. So, Green's function of a wave equation in curved space time, that is the quantity that should replace the delta S square A B, and not the delta of S square literally generalized from flat space time. So, this should go to something like G I A I B d A I A d B I B, that is, take the two indices if for a curves for a vector Green's function. This is a scalar Green's function. You can have a vector Green's function similarly defined, and if you do that, you can come to this formulation. Now you can ask yourself, what does this look like? Does it look like the delta function that we were looking for? So the answer is the following. The Green's function has two, let us take this x, and no, this is a rather, and let us suppose this is x, or take a general point x. So the Green's function will be defined as a vector at each point x and a, and when you ask what is its functional form, this can be shown in general that it is made up of a delta function, delta s square that we were looking for in the first place. Let us multiply it by some function plus f g h, let us say h times theta of s square. This is the Heaviside function. That is, if you remember, theta of x is equal to 1 for x greater than 0 and 0 for x less than 0. This is the Heaviside function. So the connector to the two ends, like we had here, what it tells you is that the action propagates mainly along the delta function part, but there is a slow part coming through theta function, that is inside the light cone. See, so you have therefore two components of the interaction, action at a distance. One is going sharply along the speed of light, and the other is going at a slower speed. And what one is asked to do is to interpret first why this thing is coming, and that can be interpreted as gravitational scattering. That is, you can imagine the light cone. Let us take the future light cone. Now, if something is going here, the light is scattered, it goes inside, it gets scattered again. So, this multiple scattering will make light go slower than the light which went straight along this term. So, you are therefore saying that the action at a distance is along light rays, but part of the light ray is going straight as light should along the null geodesic, but part of it goes slower than the typical light speed because of scattering. So, once you do this, it works out all right, and you can write the formalism in curved space time. I will not go into that here because that will take me too far away from the essential action at a distance electrodynamics, but I wanted to point this out to emphasize that the generalization can be done, but you have to extend your horizon a little. You have to think of gravitational scattering, which is not present in flat space time because there is no gravity involved in that framework. So, I will leave that topic now and come to something different. Yes, I am now coming to quantization issues about which I mentioned earlier, the problems which Feynman was trying to tackle, and in the course of which he invented a lot of interesting things like Feynman diagrams, path integral and so on. But eventually he had to switch to field theory because he found that he could not quantize the action at a distance. So, here I have mentioned some new interpretation that can be given, but I will come back to this before long, but I will now today talk about a particular problem which people claim that to solve that problem you need quantum field theory. So, if you say you need quantum field theory, that means you need fields, and if that fields are needed, it means you are giving up on action at a distance. This is the normal approach. So, what we have to show is that in this particular case you do not need field theory, and what that case is the spontaneous transition of an electron, atomic electron, from a higher energy state to lower energy state. So, here I have the following: imagine 3 levels E0, E1, E2 of an electron in an atom. These are energy levels, so that this is higher than this is higher than that, and you have the electron here in the middle level. Now, that electron might decide under quantum effects, it decide to go up here at E2, or it could go to a lower level E0 from E1. So, there are these possibilities, three possibilities: either it stays here, continues to stay here, or it decides to jump up, or it decides to jump down. That is logically the 3 possibilities for the electron. The question is, what is physics of quantum theory telling it to do? So, this is what we want to work out, and let us see whether here one could argue that compute probabilities for the processes A, B, C, which I had outlined here, stay where you are, go up or go down. So, on the assumption that there is no stimulating electric field on the electron. Now, we are talking of spontaneous transition of an electron down. Now, let me come to that first. If you take an electron, these are the 3 levels, and supposing the electron spontaneously jumps down. Now, this or it could jump up if you did not know the answer before and what it is going to do. Theory tells us that it should jump down, and there is a certain probability that it jumps down and certain probability that it continues to stay here, but it does not go up. Now, normally what happens is, if there is an electromagnetic field around, that field will push the electron up or down. There could be induced transition of the electron down or up, induced by the field that is present. Now, if that induced field is 0, the answer should be that the electron should continue to stay there, but it does not happen, the electron jumps down, and the answer and that is explained in field theory by saying that even if the lowest energy state of 0 quanta of this induced radiation, there is still a vacuum fluctuation. The vacuum is non-trivial in the sense that the vacuum has something going on, and that vacuum fluctuation has electromagnetic changes going on, and those interact with the electron and make it jump down. Now, if you make that statement, you are therefore allowing for essentially the state of vacuum fields, because that is where it in the quantum field theory you get this n plus half and this half h omega is the kind of vacuum effect that one invokes. When you are doing action at a distance, you cannot talk of this half n plus half and all this, because all this machinery has come from field theory. So, field quantization, it is put in sometimes when you write down the rules of quantizing the electromagnetic field, you use this commutation relations and so forth in quantum theory. Now, here what we can do in action at a distance is the following. Let me go to the classical result which we had the following. I will remind you of this is the typical electric charge A is affected by the rest of the particles in the universe by a full retarded field coming from all B not equal to A together with this radiative reaction. This is what our classical theory tells us. So, if we are looking for the quantum version of this result, then we could say that this part is the standard induced interaction. The induced field which was knocking the electron up or down, that part is served by this result, because that is the field coming from other particle. But what do you say about this? Because this thing apparently comes from I mean it is defined in terms of the charge A. So, it looks like a self action term, but it is not self action. We saw that this term comes from the rest of the universe, the response by the rest of the universe. So, what we have to do is hope that the induced the spontaneous transition probability will come from this term by applying the response term suitably to this particular problem. So, what we have to do is basically have this possibility. Supposing you take a electron sitting here and imagine that it goes up. There is no harm in allowing it the full freedom either to stay here, to go up or go down, and say that we will determine the probabilities for each process depending on what physics is available to us. So, if you send this thing up, you can then do a calculation of the following kind, that this interaction will produce a retarded field, and that retarded field will go up in the future, interact with the absorber and will instantaneously bring back a reaction which is what we call the response of the universe. So, that is going to act on this charge simultaneously. So, while it is going up, it is also getting the reason why it is going up is because that from the future the interaction is going to hit it instantly. So, there is a, you may think what is happening first, is the charge moving first or is the interaction coming from future first. Same thing here, there is a possibility that it can go down. So, if it goes down, it will produce an interaction in all directions, and it will go in the future, interact and bring back a response, and it was that response which was driving this down. So, you have a kind of a self consistency cycle, and you have to say that I have got these two possibilities and I want to compute the probabilities of doing this in each case, and the one the probabilities will decide what actually happens. And if you do compute the probabilities, I will come to that how this is done very briefly. But if you do assume that you are able to compute the probabilities, the answer that comes out is the following, that the probability of this going up is 0, but the probability of it going down is finite, and it is the same probability that you compute from field theory for spontaneous transition. So, you can see it in this following way, that this term has a specific sign, it is not time symmetric. If it were time symmetric, then you could have written it retarded in advanced minus retarded. If it were advanced minus retarded instead of retarded minus advanced, then your calculation would have given you this as a outcome of this interaction. You would have spontaneous transition upwards, which is not found. So, you find that everything works in a self consistent manner. The question is how actually you compute this probability. So, here I want to say something compute probabilities for processes A, B and C. Sorry, what happened? Yeah. So, you have compute the probabilities for the processes A, B, C on the assumption that there is no stimulating electric field on the electron. The state of 0 quanta of a field, that is the one we are corresponding here in action at a distance. Assume also that the universe gives the correct classical response, that is perfect future absorber and imperfect past absorber. So, that we get this particular thing which I have shown on the board. So, then you have to find these probabilities by calculation. So, what happens is that you get the right answer because of this term here, and the extra degrees of freedom ascribed to a field are not needed. So, normally one assumes that vacuum is having a half quantum for the field, the 0 state. So, the response of the universe instead plays that role. The response of the universe appears as an influence functional, which can be written as follows. So, now I want to say something about the path integral formulation which Feynman had used. So, briefly I will say what the path integral formulation does. If you take the classical physics derived from action principle, the classical laws are given by principle of least action or stationary action, and this is given by delta S equal to 0. Now, Dirac had wondered about why you have a classical rule like this. How do you rationalize it? From where did this rule come from? You find a discussion of this in his book on quantum mechanics, the classic book which introduced quantum mechanics. So, Feynman was very much impressed by his argument, Dirac's argument, and this, what Dirac hinted was that this is following from h equal to 0. That means, if you put Planck constant equal to 0, then that means you are in classical domain. If you have non-zero Planck constant, then uncertainty principle cannot be avoided and you are in the quantum regime. So, to avoid that, in a purely classical situation, you put h equal to 0, or you can say that S is, or you can say S large compared to H cross. This if you are in this approximation, you say that this means that the path integral, which means that the path chosen by the system will be given by principle of least action. So, this was what Dirac said. Now, Feynman took this much further, and his argument is like this, that if you suppose you start from state 1 and go into state 2, then the classical path has got delta S equal to 0. For example, if you are talking of a free particle going from 1 to 2, state 2, if these states are specified and it is a free particle under no forces, then Newton's law of motion will tell you that there is 0 acceleration, and you can fix this path accordingly. So, given the classical rules, you can fix a given path. Now, supposing you do not allow monopoly to the classical solution. Classical solution is one amongst many. So, you can have other paths going from here to there, not satisfying delta S equal to 0. So, what you do is you say that this can be ascribed a probability amplitude E s over h cross. So, this is the formula or rule which Feynman introduced. He said that if you take any, first of all you allow all paths geometrically possible, and you allow each path to describe the transition from state 1 to state 2, but attach a probability amplitude e to the power s over h cross, and then that way you will be able to arrive at this result. Now, how do you arrive at that result? So, you sum over this for all paths from going from 1 to 2, assuming that such a sum exists. So, you make the assumption of everything being well behaved and the integral being defined. So, this summation over all paths is what is called the path integral, path integration. So, all these paths, just as you integrate a function f of x dx by saying that x goes from say 0 to 1. So, here you are saying that you are, instead of having f of gamma d gamma, that is gamma is a path, and to indicate that this is not a ordinary integral, Feynman used this notation of a thick integral, the fat integral, because it combines lot of paths in one. So, a lot of points in one. So, you have therefore, this situation. Now, we can see what happens in this assumption, S going to large compared to H cross. What happens is the following, that the when you sum over things, if you let H cross go to 0, what will happen is S over H cross will be a very large number, and if you take e to the I times some very large number, ideally infinity, but let us take this to be very large number, it is oscillating very rapidly, this term. It will be of magnitude 1, this is always equal to 1, it is a complex number which is 1, but it is oscillating very rapidly. And so, if you sum over such things, these oscillating numbers will give you 0. So, you will ideally get 0, except in an situation where some of these oscillations are all coherent, they are all going in the same direction. So, supposing this is one oscillation, another oscillation is this. So, these will tend to cancel each other. But supposing you had oscillation like this, another one is also going like this, then these will all combine together to give you some finite non-zero answer. And that is what happens in the path integral theory, that if you have delta S equal to 0, that means those neighboring S values are the same, then there is a coherent addition of these oscillations, and you therefore get basically a finite answer, non-zero answer, and that answer is the classical path you are talking of. So, because we have gone to S greater than H cross, so we are in the classical limit. So, in the classical limit, it will pick out only that that value of S which is satisfying delta S equal to 0, and all those coherent paths will combine, and that is why you get the principle of least action. So, it was a very nice explanation of a classical principle which was being followed as a kind of ritual by physicists. They found that it worked in so many different contexts. So, if you have dynamics and you do this, you will get Newton's laws of motion or Lagrange's equations. If you do it in electrodynamics, then you will get Maxwell-Lorentz equations. So, everything works in a kind of mysterious way, that this process, if you follow, will give the answer. But you could not see what its relationship was to quantum mechanics, and how the quantum and classical limits can be reconciled in terms of this approach. So, that is what I wanted to emphasize here, and let us now go further. So, the response of the universe, now this is another jargon that I want to explain. The response of the universe appears as an influence functional which is written down for any pair of interacting electrons. So, let me go to that one. This is the influence functional. So, let me say what is happening here. Imagine that there are two electrons A and B which have their world lines, and they interact with each other, and this interaction, when you use the action at a distance form, you can do a kind of Fourier analysis for that delta S, the S squares which come in the expression. So, you find that this F is coming like this, and what does this mean, this whole expression? this is coming in the same way as this here. If you look at the board, you have a classical response of the universe, which can be translated into quantum response if and it will appear, that response will appear as an external force like this. Here it is A and B are different, there it will be just A. So, all these B's will also be written to A. So, you will get some kind of double integrals. So, when you do this, you find that there are interactions between first of all, you are talking about something which is multiplied by its complex conjugate, and that means you are talking about probability per se rather than amplitude. So, this F A, this influence functional, is like an external force acting on a system. So, you imagine a charge A going by itself, it will not have any interaction with anything else, but if you put it in charge in connection with the rest of the universe, then these responses will come from the universe, and those can be summarized in terms of this kind of integral. So, the quantum electrodynamics based on F here explains all the observed phenomena between electrons and photons on par with quantum field theory. So, once you derive this formula, you can show to a field theorist that this is what any pair of electrons will do when they interact with each other, and this same formula is derivable from quantum field theory. So, here you can do this without appealing to field theory, and including, that is why I put here, because people always ask what about lamp shift, because lamp shift is something which really brings in the field characteristics. So, including lamp shift and anomalous magnetic moment of the electron. Normally, you would expect the electron to have a certain magnetic moment proportional to h cross, but you actually observe something extra, and that extra comes from interaction with, supposedly with vacuum, and in terms of these 0 point energy and so forth. But here you can get it all, the lamp shift results, by interaction through the rest of the universe. So, what one has to learn in dealing with this is to this action at a distance is to appreciate the fact that the universal response is a key role, plays a key role in this whole matter. Now, when Feynman was doing his attempts to quantize, he did not have the response of the universe as a vital ingredient, because cosmology was not being considered by him at all in this process. Everything was locally done through thermodynamics. So, this does not happen. So, I just want to go back now here. If you want to see all the details which I have skipped over, otherwise you will have run away long back, because it is become quite intricate, but it can be all worked out. So, the path integral formulation by Feynman for non-relativistic electron can be extended to relativistic one. Now, this is also something which you do not find done by Feynman. In Feynman and Hibbs' book, they are mostly non-relativistic, but he gives some hint somewhere for how to do it for relativistic electrons. So, let me just briefly mention what happens. If you look at the electron going in a relativistic way, you do not make it go like this, but it goes in a kind of zigzag fashion, and each of these are null sectors. So, you can make a what you call track from any point A to any point B, and you want a relativistic electron to go from A to B. What you do is that relativistic electron has eigenvalues plus minus C, forward or backward in any given direction. And this was in fact derived by Dirac when he was writing down his Dirac equation. He showed that the eigenvalue was C, and at that time it was a little mysterious why the electron relativistically must move with velocity plus minus C. Of course, Dirac rationalized it by saying that when you do this averaging, you can get any non-relativistic velocity, because it is not all the time going in one direction. So, this was possible, and you can use the path integral extension to relativistic electrons, and this can be put into the theory. And then what about closed loops, because they also come in some kind of mysterious vacuum interaction in field theory. So, here what happens is the following. If you see here, two electrons, one goes from 1 to 3 and the second goes from 4 to 2. Now, you use this symmetry of interchange between two electrons, because all the expressions have to be symmetrized between two fermions. So, what happens then is 1 goes to 2 and 4 goes to 3. So, this figure goes to this. In the same way, if you had an electron 1 to 3, 3 to 4 to 2, you again do this kind of interchange. You find 1 goes to 2 and 3 and 4 form a closed loop. So, you can get closed loops in this fashion. And as I said earlier, the spontaneous downward transition of an atomic electron explained as the outcome of outcome of the response of the universe. So, what I want to do is, I think before I go to this, yes, coming to this particular aspect, this influence functional that is defined here is basically telling us the interaction between any two electrons, and if you are able to show that your result agrees with field theory, then you should be able to explain all aspects of QED. But I want to now end by talking of one particular point which we have not I have not yet brought out clearly, and that is the following. You see, classically we said that if this is an electron, let us call it A, then it cannot have any self action. That is the Wheeler-Feynman prescription or Fokker action. So, and in fact, you can see that if this is a time-like line, you cannot have a connection which will give you a delta of S square. That means, you cannot have a any 2 points on it connectable by a light ray. So, you have here a situation that there is no self action, but what happens in the quantum domain, is the following: you cannot avoid this kind of self action because for the following reasons. Supposing you take 2 electrons, now here we say that these 2 electrons are different and therefore, they are interacting. But once you adopt the religion of quantum mechanics, all the assumptions of quantum mechanics, then you know that there is this there are these indistinguishable particles. So, this is indistinguishable from this. So, to some extent it is not possible for you to argue that whether this is interacting with this or not, because you can have a situation where you are seeing 2 bits. If you say they are interacting and because of this backward forward going in time, it could have this sort of thing. Now, this does not look like going inside the light cone, it is coming out of the light cone, but the fact is you can say that this is like electron positron pair and they are annihilating, creating. So, you can have an electron annihilating and recreating, and in the vacuum all these processes go on in general. So, here also this electron might or might not interact. If you say if it is connectable, if it is part of the same electron, then it should not interact, and if it is not, then it should interact. Then this is something you cannot decide simply by looking at these 2 pieces. So, you have to allow all these to interact. So, you cannot avoid self action in the sense of classical electrodynamics. You must have self action in general, but you can of course say that if you take just these 2 bits, then there is delta of S square will be equal to 0. So, the point that one has to take into account is the fact that when you take an electron, then these any 2 points can in principle interact. In the you can think of it that there may be in the vacuum lot of things happening, and that is connecting this point to this point by electrodynamic interaction. So, you could therefore have self action, and that self action would produce this lamp shift and various other anomalous magnetic moment effect. Now, in my next lecture I will indicate how this self action is controllable. That means, you do not need to have divergent integrals arising from such a self action, and you can in fact get a finite answer for the mass of the electron and the charge of the electron. So, what you call delta m, delta E, the mass and charge arising from interaction with the vacuum and other particles. This effect is finite. So, this comes because of the boundary conditions at cosmology. So, again I will show how this can be derived, or at least one can see the logic behind it, and then I think that will show how why action at a distance can be given a kind of independent status, that is giving out something which is not simply repeating what field theory does, but is doing something which field theory could not do, namely the renormalization without infinities. So, I will come to this in my next talk.
Any questions?
So in the beginning when you started out, when you went to curved space, so in curved space, of course, connecting 2 points, you can have more than one geodesic which follows this delta S square equal to 0.
In curved space, you can have many strange things which you don't expect in flat space. But normally, if you take curved space of the kind which is produced by Schwarzschild space-time or black hole type of thing, then you don't get these strange geometrical things unless you go very close to the horizon and so on. But one will have to investigate in such situations what happens to electrodynamics or any other thing. Things would happen strangely for field theory also, because you are dealing with at horizon with what you call strange propagation of signals, one-way propagation and light being held up at the horizon. So, all these things would need to be looked at much more carefully. I mean, it's not just the action at a distance, but field theory also.
So in your formalism, you have assumed that there's only one particular geodesic connecting 2 points, like whatever.
Yeah, if you are asking between any 2 points in curved space, how many ways you can connect, how many geodesics you can draw between them. Yeah, answer is normally you expect one geodesic connecting 2 points, but you could have more than one in some strange geometries. Like you can go around this way and go around this way.
So my question is your formalism applicable if there are more than one?
I think it is applicable, but you have to take note of the fact that there are more than one geodesics. So when you consider the point A or point B, how they are converging, the geodesics are converging there. That convergence factor is also built into that formula, and that has to be taken into account. It may be behaving strangely in some cases.
Any other questions?
I have a
Yes.
slightly unrelated remark. You mentioned about Feynman's path integral formalism of
Yes.
quantum mechanics. There is a paper dates both Schrodinger's as well as Heisenberg's paper on quantum mechanics, where Gregor Wenzel actually formulates the essence of the path integral formalism. Where he does is essentially more or less the same kind of a thing. Problem is scattering of an absorber, and he in fact claims that by knowing a particular rule for phase of the various paths for a transition needs to be added, not the amplitude squared, the probabilities, but the probability amplitudes must be added.
I see.
And that is the remarkably enough,
Yeah, when
this
was
is
this?
all the seeds of Feynman path
Yeah,
integral.
when was this done?
This is just about a year before both the papers. In fact, I have a sequence of
I
all
see.
the
I
three
would like
papers.
to see that.
And Gregor's paper seems to more or less predates the thing. But surprisingly enough, there is no reference to Wenzel as the person who is responsible for the Feynman path integral, which in fact Feynman refers to Dirac's paper.
Yes, yes. Okay. Yeah, I would like to get some. Yeah.
Thank you. Are there any other questions? Okay, if not, let's thank the speaker again.
Okay.